The gradient here runs at 1 in 40, 39 tunnels cut through the Sierra Nevada, between Roseville and Sparks, Nevada. Nearly 40 miles of timber, snow sheds seal the track against avalanche and blizzard. Inside those structures, in winter, the air turns to smoke and carbon and suffocating heat. Conventional locomotives had been nearly killing their crews on this mountain for 30 years. But this locomotive is not facing the mountain in the conventional way. The cab is at the front. The boiler is behind it. The exhaust stack is at the rear. 219 tons in working order, running backwards through the rock and smoke of the Sierra Nevada. When the first cab-forward crews reported for duty in the winter of 1910, some of them refused to board. They had heard what the engineering community was saying. Pressurized fuel oil piped from the rear-mounted tender to a firebox positioned at the very front of the locomotive. Any failure in that fuel line, anywhere along its length, would spray oil across hot metal at operating temperature. They said it would burn. They said it would explode. For 46 years, they were wrong. The Southern Pacific's problem in 1908 was specific, geographical, and lethal. Locomotives working Donner Pass operated inside snow sheds and tunnels for miles at a stretch at full regulator. Exhaust gases reached lethal concentrations. Crews had resorted to running locomotives backward, tender leading, to put the smoke behind them. It worked for breathing. It destroyed visibility, stressed tenders not designed to be pushed at speed, and forced every engineer to work from the wrong side of the cab. The engineering department proposed a permanent solution: design the locomotive that way from the beginning. The cab at the front, the firebox at the front, the smoke box at the rear where it could exhaust behind the train. To feed the fire, oil under 5 pounds per square inch of air pressure would travel the full length of the locomotive through a dedicated fuel line. Southern Pacific ordered 15 from Baldwin Locomotive Works in 1909. Not one was tested before delivery. Before we continue, if this kind of railway history matters to you, consider subscribing to the channel. Every video here is built around the locomotives and railway systems that the standard histories overlooked, the machines that outperformed their celebrated counterparts, the engineering decisions that were ahead of their time, us and the railway lines that shaped nations without receiving the recognition they deserved. If that is the kind of documentary worth watching to you, the subscribe button is how you tell us, and we want to hear from you. Did you work on the railways? As a driver, a fireman, a fitter, a signalman, a track engineer? Did a parent or grandparent spend their career on a railway that is no longer operating, on a locomotive class that is no longer preserved, or in a workshop that is no longer standing? Leave it in the comments. The people who actually operated these machines know things that do not appear in any published railway history. We want to hear from them. Now, back to the locomotive. The MC2 class entered service in early 1910 as Compound 2882 Articulateds, built by Baldwin Locomotive Works. High-pressure cylinders, 26 inches bore, 30 inches stroke. Low-pressure cylinders, 40 inches in diameter, essential for the compound expansion that extracted every remaining unit of energy from the steam before exhaust. Working pressure was 200 pounds per square inch. Tractive effort was rated at 94,880 pounds force. In working order, 437,000 pounds, nearly 219 tons. The fuel system was the engineering concern that crystallized opposition. The tender oil bunker was made airtight and structurally braced. Air from the locomotive's main reservoir pressurized it at 5 pounds per square inch. From there, oil flowed under this pressure through a dedicated line along the full length of the locomotive to the firebox at the front. On upgrade, when gravity worked directly against the flow over the entire length of the engine, that 5 pounds of air pressure was what kept the fire burning. If the line fractured anywhere, over the running gear, past the articulation joint, through the snow shed, pressurized oil would spray across hot running surfaces at operating temperature. There was also the backblast. A flame failure at the front of a long locomotive meant oil had to travel the full length of the engine before it could be shut off. In the delay, unburned fuel accumulated. When the flame caught again, the result could be violent. These were not invented risks. They appeared in technical engineering journals. The MC2 went to work in the Sierra Nevada anyway. What the operating record showed was different from what had been predicted. The fuel system worked, made the pressurized oil delivered consistently up the grade and through the tunnels. The backblast risk proved manageable in practice, a documented nuisance, occasionally alarming, but not the catastrophe that had been forecast in the technical press. And the crews who had initially refused to board made a discovery that no drawing board engineer had fully measured. Sitting at the front of the train in clean air, with an unobstructed view down 30 miles of open mountain track, was a different kind of working life entirely. The design was successful enough that the Southern Pacific built on it continuously for 3 decades. The AC-4 class arrived in 1928. Larger 488-2 simple articulateds, designed to move faster freight against road haulage competition. Then the AC-6, the AC-7, the AC-10. In the middle of the Second World War, the AC-12. By that final class, the dimensions had grown substantially. 4 cylinders, 24 inches bore by 32 stroke. Working pressure, 250 pounds per square inch. Tractive effort, 124,300 pounds force. Locomotive weight, 657,900 pounds, 328 tons without the tender. The engineering community that had predicted explosion and fire received 46 years of mountain service instead. 256 locomotives. No other major North American railroad ever built one. The last cab forward in revenue service was AC-10 number 4211. It made its final run on November 30th, 1956. From Oakland to Davis with a caboose behind it. The steam era on the Southern Pacific was finished. Diesels had taken the mountain. The cab forward, the locomotive too dangerous to ride, too unconventional to trust, had kept its crews breathing on a mountain that had been trying to kill them for 30 years. Through 39 tunnels, through 40 miles of snow shed, through 2 world wars, through the entire transformation of American freight traffic, from steam to diesel. No other major North American railroad built one. The design's logic was inseparable from the Southern Pacific's specific geography. Elsewhere, it was unnecessary. On the Sierra Nevada, it was the engineering answer to a specific, documented, lethal operational problem. And it answered it, without the fire, without the explosion, Without the catastrophic failure of the pressurized fuel line that had been forecast with such certainty in the technical journals of 1909. The engineering record shows what the standard histories do not always state plainly. The most radical-seeming design on the American railroad, the one that put the crew in front of the boiler with pressurized oil running the length of the machine, was the safest way to work that mountain. 256 locomotives, 46 years, not one explosion. If this is the kind of railway history you want to keep watching, subscribe to the channel. There are more locomotives, more railway systems, and more engineering achievements still to document. And if you have a connection to what you just watched, a family member who drove this class, worked in the workshops that maintained it, or operated on the railway that deployed it, tell us in the comments. What did they drive? Which railway, which depot, which line? Sonny, the people who operated these machines are not in the standard histories, but the engineering record depends on what they remember. We want to hear from them.